Okay, next we're going to talk about, we're just looking at some manipulations with imaginary and complex numbers. A lot of you are familiar with the I's. And I found some interesting things online at askmathematician.com. And one quote from a physicist and another from a mathematician. And in both, it basically, working with these complex numbers allows us to figure out the things that we want to figure out. The physicist said, quote, what did he say? In quantum theory, you'll find that on the most fundamental level, the universe seems to prefer complex numbers to real numbers, but you can't use them to count. So most people can live long, happy lives without, but of course, we wouldn't call that living. And the mathematician gives, the more mathematician type answer, which is basically, a lot of the things that we do or a lot of things that we learn is so that we can do more, basically. So as we're going through, first of all, how an imaginary number is defined. Okay, the square root of any negative number is an imaginary number. By definition, the square root of -1 is I, and also I squared is -1. And based on what we've talked about with square roots, if I ask you to simplify the square root of -1, I'm saying find something that I can multiply 2 times to get -1. If the number that I multiply twice to get -1 is I, then it should be that if I multiply I twice, that I do get -1. And with what we're going to be working with, you're never going to do left to right. If you have something that involves a square root of a negative, you're always going to put it in terms of I. If you see an I squared, you're always going to rewrite it as -1. You won't be taking -1 and rewriting it as I squared, or taking I and rewriting it as -1. You'll just be moving left to right with these identities. So if I want to express this square root of -80 in terms of I, we've talked about our product rule. And if we think about that, -80 is the same as -1 times 80. So this is the same thing as the square root of -1 times the square root of 80. By definition, the square root of -1 is I. Okay? If you just write I root 80, that is not fully simplified. So everything that we've been doing up to this point still applies as well. If you have a radical expression and your radicand, which is 80 in this case, is divisible by a perfect square, you do need to go ahead and do that simplification. So the square root of 80 is divisible by 16, so this is the square root of 16 times the square root of 5. Square root of 16 is 4, so that would be 4 root 5. So putting it all together, the square root of -80, don't forget we have this I here, we write that typically as 4I root 5. Okay? You can also write it as 4 root 5I. You just have to be careful that you don't, if you write it this way, you don't want to have that I underneath the square root, which is typically why we go for this route instead. But some people want you to write your imaginary numbers with the real number coefficient first. So the 4 root 5, then the I. But this is really probably the most standard way. And actually, when I'm going through these simplifications, I would never do what I just showed you. I would never split it up into the square root of -1 times the square root of 80. Instead, I would just say, okay, well, I know it's going to have an I, so I would put the perfect square and the negative together. So I would break it into the square root of negative 16 times 5, because still negative 16 times 5 is negative 80. And so the square root of negative 16 is 4i, and then we have our remaining root 5. So, if it's a square root of a positive number, no I. If it's a square root of a negative number, you will have an I. Okay, square root of 16 is 4. The square root of negative 16 is 4i. The square root of 9 is 3. The square root of negative 9 is 3i, and so on. Okay, same thing here. Express this in terms of I. So we're trying to decide if there is a perfect square that goes into 735. So if I just start thinking about my perfect squares, 1, 2 squared is 4, 3 squared is 9, 4 squared 16, 25, 36, 49, 64, 81, 100, 11 squared is 121, 12 squared 144, 13 is 169, and so on and so on and so on. And with the big numbers, it gets a little bit, there's a lot more to check. So it might be best to try to just start breaking it down. The fact that it ends in 5, I know that it is divisible by 5. So if I take 735 and divide that by 5, I get 147. And that helps me because I know that 49 goes into 147. That would be 49 times 3 would give me 147. So 735 is divisible by that perfect square 49. And what I have so far is that 735 is 49 times 5 times 3, and the 5 times 15, or 5 times 3, I can just rewrite as 15. So if I do 49 times 15, I will get 735. So going back to my simplification, I have my negative. I need to leave that in front. And that's times the square root of negative 49 times my 15. Okay? Or I can go ahead and break it apart. That's the square root of negative 49 times the square root of 15. So I've got my negative, bringing it down. The square root of negative 49 is 7i, and I have my root 15 remaining. I can't do anything to simplify this because 15 is not divisible by a perfect square. I know I have it broken down as much as I can. So this is how I will do that simplification, or how I will express that in terms of I. And the reason that we're saying express this in terms of I is because before, when we looked at things like this, we would say, if I asked you to do square root of negative 25, for example, we just said it's not a real number. Okay? And now with the discussion that we're having, you can see, no, it's not a real number. It is an imaginary number. So saying express in terms of I, if those are the directions, then you know that I do want you to put this in terms of I rather than just saying not a real number. Okay? Doing this multiplication, if you go back to when we were talking about multiplication of radicals and this product rule for radicals, I gave you two options. Okay, the first option was that you could multiply first, then simplify, and then the second option I gave you was, okay, well, we can simplify first and then multiply. And at the time, we said, well, most of the time, it's going to be most beneficial for us to go ahead and do it this way, where we'll multiply together and then simplify. But there are some instances where this is not an option, and this is one of those instances. Okay? It is not going to be an option for us to multiply and then simplify when both of our radicands are negative. Okay? And that's because both of our radicands are negative. Okay, the product rule for radicals says that for any root n, if the nth root of a and the nth root of b are real, then this product rule applies. Then this times this, the nth root of a times the nth root of b is the nth root of ab, or what you would get when you multiply. These are not real numbers, so this product rule for radicals, we cannot use this because they are not both real numbers. So we have to simplify first, and then we can multiply them together. So 25 is a perfect square. The square root of 25 is 5, so the square root of negative 25 is 5i, times 18 is not a perfect square, but 18 is divisible by the perfect square 9. So I would rewrite this, break it up as the square root of negative 9 times 2. The square root of negative 9 is 3i. And so the square root of negative 18 is 3i root 2. So this became 5i, and this became 3i root 2. And now that we have the simplification done, now we can go ahead and multiply. And so when we do, we multiply coefficients together. 5i times 3i is 15i squared. And then we tack on our root 2. And if you go back to the first slide, or second slide, I said if we've got the square root of a negative 1, we'll always write it as I. And if we have an I squared, we'll always rewrite that as a negative 1. So where we are in this problem, we have 15I squared root 2. We need to take this I squared and write it as its equivalent, which is negative 1. So this is the same as 15 times negative 1 times the square root of 2, or negative 15 root 2. Okay? If you would have tried to do it this way, using option 1, you would have ended up with an answer of positive 15 root 2 rather than a negative 15 root 2. Okay? Trying another one. Again, since both of these radicands are negative, I know that I must first simplify each of my roots. So I've got square root of negative 27 times the square root of negative 50. I can simplify 27 is divisible by 9, the perfect square. So I'll break that into the square root of negative 9 times the square root of 3. Again, remember that these two must multiply to this. Same thing over here with 50. If I'm trying to decide if there is a perfect square that goes evenly into 50, that number is 25. So I'll break this into the square root of negative 25 times the square root of 2. And don't forget that we're going to then multiply these values together. So the square root of negative 27 is equivalent to 3i root 3. The square root of negative 50, when I simplify here, I get 5i root 2. And now I can multiply these together. So I multiply coefficients, and then I multiply my radicands. So 3i times 5i, I get 15i squared. And the square root of 3 times the square root of 2 is the square root of 6. We're almost there. The only issue at this point is this I squared. Multiplying by I squared is the same as multiplying by -1. So this is -15 root 6. Something to keep in mind as you're going through your homework, if after you've done this simplifying and multiplying, it may be that the product of these two creates a number that is divisible by a perfect square, or creates a number that is a perfect square, one of the two. So if you end up with either a perfect square or a number that is divisible by a perfect square, you do have to go ahead and simplify again. Because 6 is not divisible by a perfect square, I know that I have fully simplified this expression. When we're looking at adding, subtracting, multiplying, and dividing complex numbers, the add, subtract, and multiply should be very similar to what you would be used to. And we'll get into that more. Dividing is not what we typically think of as dividing. A complex number. So we've been talking about just imaginary when we take the square root of a negative. But a complex number is a number that can be written in this form, a plus bi, where a and b are both real numbers. Okay? So the set of imaginary numbers and the set of real numbers are also subsets of the complex. So let's look at this up here. If a is 0, which 0 is a real number, then my number would look something like this. And so it would just be an imaginary number. If my b was 0, then this term would not be here, and what I would have is a real number. So within the set of complex numbers, you have complex numbers, you have real numbers, which are complex numbers, and you also have imaginary. So, we are in an even bigger set than the real numbers, or we're in a set that houses the real numbers. Doing a subtraction. So if I want to take this complex number and subtract this complex number, we can say, a lot of times we say, well, this is the real part and this is the imaginary part. And so when you're working with addition or subtraction of complex numbers, you can, depending on the sign, add or subtract the real parts, add or subtract the imaginary parts. What it boils down to in terms of manipulations is that you would treat these complex numbers as in the same way you would treat a binomial that had a variable x. Okay? I is not a variable, but we do treat it in the same way in our algebraic manipulations. So to do this subtraction, I have to subtract both the real part and the imaginary part. I have to basically distribute that minus. So rewriting, I have 13 plus 11i minus 6 minus 2i. So if I take the 13 minus the 6, that gives me 7. The 11i minus the 2i is a positive 9i, so plus 9i. So subtracting those complex numbers gives me the complex number 7 plus 9i. Again, multiplying two complex numbers to multiply this by this, you would do it in the same way you would multiply binomials, and that is to FOIL. Okay, so first times first, 5i times 4i. So if you multiply the 5 and the 4, you get 20. The I times the I is I squared. So the first term is 20i squared. Outer times outer, 5i times negative 5, it's negative 25i. We've got minus 25i. Inner times inner, ignore that. Positive 4 times 4i is 16i, so plus 16i. And then last times last is minus 20. After we've gone through the FOIL process, we still need to do any simplification. Combine any like terms. These two are like. And then also, remember, when we see I squared, we need to write it as negative 1. I stay. You see an I, you leave an I. But an I squared, you need to write that as negative 1. So 20 times negative 1, this is 20 times I squared, so 20 times negative 1, we've got negative 20. Our negative 25i plus 16i, we just add or combine our coefficients. Negative 25 plus 16 is negative 9. So minus 9i minus 20. And then now we can combine our constants, or the real parts here. Negative 20 minus 20, we have negative 40. So negative 40 minus 9i is the resulting complex number. Division. So as I was saying, division is not like what we're used to. You don't actually divide, but rather you rationalize. And the concept is, we were talking before, this last chapter, earlier in this chapter, traditionally speaking, when we write a fraction, we want to write it with a rational number in the denominator. This is a complex number. If you've got an I in there, it is not a rational number. So to rationalize, we are going to have to rewrite an equivalent fraction that doesn't have an I in the denominator. And we are going to do this just as we would when we were doing our rationalizing before. If you have, this complex number in the bottom, two terms, you are going to rationalize by multiplying by the conjugate. So two terms, TWO, two terms, you're going to multiply by the conjugate to rationalize. Okay? And rationalize. We want to end up with no i's in the bottom. That's our hope. Okay? So if we take our complex division, 6i divided by 9 plus 5i, the conjugate of 9 plus 5i is 9 minus 5i. And working on the principles of equivalent fractions, if I multiply the bottom by 9 minus 5i, I have to multiply the numerator by the same value if I want to create an equivalent fraction. So now that I know what I want to multiply by, now I just do it. So in the top, I have to take this 6i and multiply by the 9 minus 5i. And just like you would if you had a monomial times a binomial, you would distribute that 6i. So we have 6i times 9 multiplied the 9 and the 6, so that's 54i. And then the 6 times 5 is 30, I times I is I squared. So in the numerator we have 54i minus 30i squared. In the denominator we can FOIL. 9 times 9 is 81. If I multiply my inner two, that's 45i. When I multiply the outer two, the 9 by the negative 5i, I get negative 45i, which adds to 0. And that's always really what you want to happen when you multiply by the conjugate. And then when we multiply last times last, the positive 5 times the negative 5 is negative 25. The I times the I is I squared. So we have minus 25i squared. Doing some simplification, so we leave i's, but I squareds, we need to make those -1. And so if I multiply, I write this in red, so this is the same thing as a multiplication by -1, as is this. So we've got 54i, 30 times -1 is -30, and minus a -30 is plus. So this will be plus 30 over 81 plus 25. So we have 54i plus 30 all over 106. Typically when you're working with complex numbers, you want to write them so that they are in a plus bi form. Okay, and you'll see these directions. To write this in a plus bi form, then you want to take this fraction and separate it out into its real part and its imaginary. So the real part would be, so it's 30 over 106 and 54 over 106i. So this would be 30 over 106 plus 54 over 106i. And as you're always expected, you should simplify that fraction. So in your calculator, just do 30 over 106 and let your calculator do that reduction for you. It is 15/53. Oops. 15 over 53 plus 54 over 106 reduces to 27 over 53. So that's 27 over 53i. And when you write the I, you want to write it so that it's on level with the fraction bar. Okay? It's okay really to put it with the 27. It's not okay to put it with the 53. But to be in a plus bi form means to have those real coefficients written out separate, or your real number coefficients. Okay? If you want to rationalize when it's a monomial in the bottom. So in the last example we had 2 terms in the denominator. In this example we only have a single term, right? There's no plus or minus. So rationalize when i's are involved. What we want to do is, when we want to figure out, is how can we get this so that we don't have I in the denominator, so that we have a rational number in the denominator. So no I in the bottom. And if we think about what we know if we have I squared, that we write I squared as -1. So I think, well, if I multiply that by I, then this is going to be 7i squared, or -7. So if you're trying to rationalize with these complex numbers and it's just an imaginary number in the bottom, you can get away with just multiplying by I, and that will take care of the I in the bottom. But don't forget, if you multiply the bottom by I, you have to multiply the top by I in order to write an equivalent fraction. Okay? When you do that multiplication in the top, you are multiplying by the entire numerator, not just the last term. So that I has to be distributed through that entire numerator. So doing our multiplication, 2 times I, we have 2I, minus 3I times I is 3I squared, all over 7I squared. That's -1, that's -1, and that's a multiplication, right? So we have 2I plus 3 over -7. And to take this complex number and put it in a plus bi form, we'll write the real part first. So the positive 3 over -7 is -3/7. Positive over negative is negative, so minus 2/7. 7th I. And the last topic that we want to talk about in this section is simplifying when we have powers of I. Okay, so we've already said if you have an I, you want to leave an I, right? And if you see an I squared, you want to write that as -1. The question now is, what do you do if it's I to a power higher than 2? And the answer is a simplified expression should never, ever, ever be written with I raised to a power higher than 1. So if you have an I, you can leave it. But if you have an I squared or an I to the third or an I to the fourth, you have to simplify it so you don't have any time, so you never have I raised to a power higher than 1. And so how would we do that? Okay, if we think about what would I to the third be equivalent to, we can use what we know about multiplication of exponential numbers. I to the third power can be created by multiplying I squared and I together. Right? If I just said, what is I squared times I, you would say, oh, well, I can, since they have the same base, I can just add their exponents. So I squared times I to the first is equivalent to I to the third. You know, we're used to doing it this way, you know, taking something that looks like this and writing it as I to the third. And now we're going the other way with it to be able to find what we want to know. And so I squared, I to the third, can be broken into I squared times I. That serves a purpose because we know I squared is -1. So rewriting that I squared is -1, and I know I can leave my I as I. So -1 times I is -I. Therefore, I to the third power simplifies to -I. Let's try I to the fourth. So I to the fourth, you know, you can do I squared and I squared. 2 plus 2 is 4. You can also do I to the third times I, because 3 plus 1 is 4. Either way, you're going to get the same thing. If you do the I squared times the I squared, you'll have then -1 times -1, which is +1. If you find the value of I to the fourth using I to the third times I, same thing. We've already determined I to the third is -I times I. We get -I squared, but I squared is just -1. So the opposite of -1 is 1. So you see, using any equivalence leads us to I to the fourth equaling 1. Okay, I'm going to write what I have off to the side because I'm getting a little sloppy. So I have I is I squared is -1, I to the third is -I, and I to the fourth is 1. So as you go through, you know, if you want to simplify I to the fifth, well, I would go to my I to the fourth because that's 1. So I'll do 4 and 1 because 4 plus 1 equals 5. I to the fourth is 1. I stays I, and 1 times I is just I. If we do I to the sixth power, maybe I to the fourth times I squared. So I to the fourth is 1, I to the second is -1, and 1 times -1 is -1. I to the seventh, maybe I to the fourth times I to the third. So that would be 1 times I to the third is -I, and that would be -I. And I don't know if you're noticing, but as we keep going, we're repeating this pattern that we've already developed. I to the 8th is I to the 4th times I to the 4th, or 1 times 1, which is 1. And as you keep going through, I to the 9th is going to be I to the 10th will be -1. It's this cyclical pattern. When doing simplifications for i's, so when we got to I to the 8th, that would equal 1. If we get to the next multiple of 4, that's also going to equal 1, right? I to the 12th would be 3 I to the 4th, I to the 4th, I to the 4th, I to the 4th, and that product would be 1. So when you're working with large powers of I, like 27, I know that if I take I and I raise it to a number or to a multiple of 4, we'll write it that way, that it's going to equal 1. And so I think about, well, 27 is not a multiple of 4. But if I wanted to split up my i's, what is the closest multiple of 4 that's less than 27? And that number would be 24. Okay? And so if I break this into I to the 24th times I to the 3rd, I know that I to the 24th is just going to be 1. And then what I have, if this is the closest multiple of 4, then what you'll have here is either I to the 1st, I to the 2nd, or I to the 3rd, which we know how to simplify. I to the 3rd is -I, and so I to the 27th is just -I. Let's do one more. Simplifying I to the 101. So I'm trying to think about how to split my i's. And what I'm going to put here is basically a number that's divisible by 4. That's what we mean when it's a multiple of 4. And not only any number, but the multiple of 4 that gets us closest to 101. And in this case, it would be 100. So that would mean 100 there and 1 i's there. I to the 100th is 1, and I to the 1st is I. So I to the 101 does simplify to simply I. So as you're going through, you cannot, if you have an I, you should leave it as I. Otherwise, you're going to have to go through some simplification. And it's not a bad idea for you to know these 4 equivalences. Though, honestly, I only just remember that I is I and I squared is -1. I know that if I know just these 2, then I can figure out any other power of I based off just I and I squared alone. So this completes our chapter. Good luck, and let me know if you have any questions.